inside a building so large it could fit an entire city block. Boeing engineers are constructing one of the most advanced structures ever created, the modern airplane wing. These wings aren't just metal panels. They're 60-meter giants capable of bending 8 meters upward while carrying hundreds of passengers through storms at 35,000 feet. Each wing contains tens of thousands of parts, miles of wiring, thousands of sensors, and must withstand forces stronger than hurricanes. Today we are going inside this unprecedented manufacturing process. And later, you'll witness the highly restricted test that determines whether a wing is truly ready for the sky. A test so extreme that only senior engineers are allowed to perform it. Before a wing can take shape, it starts as raw metal, bauxite ore mined from the earth. First, the ore is refined into alumina. Then, through powerful electrical currents in the Hall-Héroult process, pure aluminum emerges. But pure aluminum is too soft for aviation, so Boeing transforms it into aerospace-grade alloys, specifically the 7000 series. Zinc for strength, magnesium for toughness, copper for crack resistance, zirconium for fatigue protection. Massive continuous casting machines stretch the alloy into long slabs, up to 30 meters in length. These slabs are heat-treated around 480 degrees Celsius, rapidly quenched in water, then stretched using presses capable of 2,000 to 4,000 tons of force. This stabilizes the metal and prepares it for the precision of aerospace engineering.
Watch the alignment on the far side. Copy that. Moving to final position.
With the alloy prepared, the next step is carving out the skeleton of the wing, with spars, ribs, and stringers. The front and rear spars are the backbone of the wing, running nearly its entire length. These enormous pieces start as thick metal blocks. Inside Boeing's 5-axis CNC machining centers, each the size of a tennis court, computer-controlled cutters remove thousands of kilograms of excess material, leaving behind ultra-precise internal pockets. Cutting heads spin at up to 14,000 revolutions per minute, maintaining tolerances within 1/10 of a millimeter. Next come the ribs, the structures that give the wing its airfoil shape. Up to 60 ribs are machined, each with curves derived from aerodynamic profiles used in wind tunnel testing. To join the metal, Boeing uses friction stir welding, a process where a rotating tool generates heat and pressure, producing a weld stronger than the original aluminum. This is the hidden skeleton that allows the wing to endure millions of stress cycles during its lifetime. Now the outer shell takes form. The wing skins. These enormous panels, some stretching nearly 28 meters, begin as thick aluminum sheets. They're placed into a stretch-forming machine as long as a building. Hydraulic arms press the metal into the aerodynamic curves required for efficient flight. To avoid micro cracks, the metal is heated to around 150 to 200 degrees Celsius. Once formed, composite layers may be added and cured inside autoclaves. Giant pressure ovens operating at nearly 180 degrees Celsius and 7 bars of pressure. The surface is anodized and coated with Boeing's signature green chromated primer to prevent corrosion. Laser tracking systems then verify the curvature with an accuracy of just 0.02 millimeters. Only when the shape is perfect are the wing skins approved for assembly.
The tolerance on the starboard flange is showing red.
But the primary interface is green across the board. We are good to proceed.
We need to ensure
This
the
is the
spars
defining
align
moment.
perfectly with the
Assembling
laser
the
guidance
wing
system
box,
before we
the front
secure
and
the
rear
clamps.
spars are placed into an
The
enormous
tolerance is
assembly
minimal at
fixture
this
stretching
scale.
across the factory floor. Ribs are attached one by one. Stringers run along the length of the wing, adding strength and rigidity. Then, the massive upper and lower wing skins are positioned on top, creating a sealed, load-bearing structure known as the wing box. Robot drilling systems glide along the wing, drilling and riveting tens of thousands of fasteners with perfect precision. Each fastener is installed under 6 to 8 tons of pressure to ensure a flawless joint. Every hole, every rivet, every alignment point is monitored by a network of lasers and sensors. If the wing is misaligned by even 1 millimeter, the entire panel must be reworked. This is where the wing truly comes alive.
Bring her down another 2 centimeters.
Steady, steady. We are locked in.
This section is clear, good tolerances all around.
Noted. Moving to the next sequence.
The alignment is holding steady at 0.0001 micrometers.
We are green across the board. Well done.
Few people realize that the wing itself is a massive fuel tank. Depending on the aircraft, each wing can hold between 30,000 and 150,000 liters of jet fuel. Inside the wing box, Boeing installs complex systems of pumps, valves, baffles, surge tanks, and ventilation tubes. Baffles prevent fuel from sloshing. Surge tanks capture overflow. Vent tubes manage pressure changes. And an inert gas system fills the tank with nitrogen-rich air to reduce the risk of explosion. Engineers perform a pressure test, raising internal pressure to detect even the smallest leaks. Technicians crawl inside the wing with endoscopic cameras to inspect sealant and verify
Alignment
that
is
the
stable.
interior is
Proceed
perfectly
with
airtight.
securing the segment.
Fuel safety is
Confirmed.
absolute. There is no room for
Engaging
error.
fasteners now.
Pressure looks stable at 50 psi.
Confirmed. No significant drop on section 4.
Next, Boeing installs the moving parts that give the wing its unique abilities in flight. Slats extend from the front edge of the wing during takeoff and landing, increasing lift. flaps deploy from the trailing edge, transforming the wing into a high-lift device. Ailerons control the aircraft's roll, allowing pilots to turn, and spoilers disrupt airflow to help slow the aircraft during landing. Hydraulic and electromechanical actuators drive these systems, delivering precision movements of just a few millimeters, in sync with thousands of other components. Torque tubes coordinate movement across both wings. Chrome-plated rails enable smooth sliding under extreme aerodynamic loads. Every mechanism must withstand freezing temperatures, turbulence, and constant vibrations, sometimes for hundreds of thousands of flight
securing
hours.
the first bolt now.
We have stabilization at 0 degrees.
Engaging the actuator now. Monitor the sensor feedback.
Flap extension complete. How are the stress metrics?
Well within tolerance. Retracting now.
Inside the wing, Boeing installs a sophisticated network of electrical systems. Up to 100 kilometers of wiring run through each wing. Strain gauges measure bending loads. Temperature sensors track thermal expansion. Position sensors ensure flight surfaces move precisely as commanded. To prevent ice buildup at high altitudes, anti-icing systems heat the wing's leading edges. This is achieved either through hot bleed air from the engines or through specialized electric heating mats. Lightning protection is critical. A copper mesh embedded within the wing disperses the enormous energy of a lightning strike, sometimes over 30,000 amps, safely along the wing's surface. The wing must withstand and survive a direct lightning strike. This is not optional. It's a requirement.
The diagnostics are showing a slight variance right here. Yeah.
Let's reinforce that joint before the next layer goes on.
The completed wing. All systems integrated. A complex network of power, data.
Now comes the most dramatic moment of all, the wing flex test. Hydraulic jacks apply enormous upward force to the wingtip. Slowly, the wing bends higher and higher, sometimes up to 8 meters, depending on the aircraft. During this test, high-resolution sensors detect microscopic cracks as small as 1/100th of a millimeter. Load cycles are repeated millions of times, like simulating decades of turbulence, storms, and real-world stress. If the wing shows even the slightest structural flaw, the component must be redesigned or reworked.
The wing is stable.
Only when the wing passes this brutal trial is it approved for flight.
All parameters nominal. Great job, everyone.
clear on the left side. Take it down slowly.
With every test complete, the finished wing is transported to the final assembly line and joined to the fuselage.
Good. Lock it in.
From raw ore to engineered alloy to aerodynamic masterpiece, this is the birth of a wing, a structure that bends without breaking, survives lightning strikes, stores massive quantities of fuel, and carries millions of travelers safely across the sky. This is inside manufacturing, revealing how the machines that move our world are built.